This talk is about reductions and extension-based proofs. I am Faith Ellen, and this is joint work with Cayman Brussa, who is my graduate student at the University of Toronto. It's well known that there is no wait-free protocol for solving consensus in asynchronous shared memory systems where processes communicate using registers. The proof of this theorem uses a valency argument. Given a protocol that claims to solve consensus, one first proves that it has an initial configuration which is bivalent. This means that there is an execution from the configuration in which some process outputs 0, and another execution from this configuration in which some process outputs 1. Then one shows that from every bivalent configuration, there's a step by some process that results in a bivalent configuration. This implies that the protocol has an infinite execution, and hence the protocol is not wait-free. K-set agreement is a weakening of consensus that allows up to k different values to be output. It is also known that there is no wait-free protocol for solving K-set agreement in asynchronous shared memory systems where processes communicate using registers. The proofs of this result are considerably more complicated and use arguments from combinatorial topology. A natural question is whether there are simpler proofs of this result. A couple of years ago, Dan, Jim, Rutty, Jimmy, and I formalized this question by defining the class of extension-based proofs, which includes valency arguments. Then we proved that there is no extension-based proof of the impossibility of k-set agreement when k is at least 2 and n is greater than k. The other part of the title is reductions. Reductions are used throughout theoretical computer science to transform impossibility results from one task to another. Specifically, if some task T reduces to another task S, and T is impossible to solve, then so is S. Another natural question to ask is whether a reduction can be used to transform an extension-based proof from one task to another. Specifically, if task T reduces to task S, and there is an extension-based proof that T is impossible to solve, is there necessarily an extension-based proof that S is impossible to solve? Although Cayman and I didn't completely answer this question, we came very close. Specifically, we defined a larger class of proofs, which we called augmented extension-based proofs, and showed that many reductions can be used to transform an augmented extension-based proof from one task to another. We considered reductions from task T to task S, which involve solving only one instance of S, but allow processes to communicate with one another beforehand and afterwards. Formally, each process PI is given an input x sub I. The processes first solve task R1 using a known wait-free protocol. Then they solve an instance of S, where each process's input to S is its output from R1. Finally, they solve task R2 to determine their outputs using a known wait-free protocol, where each process's input to R2 is its output from S. These reductions are more general than mapping reductions, but less general than oracle reductions. An extension-based proof is a game between a prover and a protocol, which the prover is trying to show is incorrect. The prover repeatedly asks queries, and the protocol responds to them. The prover's queries can be chosen adaptively based on the responses it gets from the protocol. Initially, the prover has only reached the initial configurations of the protocol. The prover may repeatedly query the protocol by choosing a configuration C it has reached and a process P that hasn't terminated in C. The protocol responds with what happens when P takes one step starting from C. It describes the resulting configuration C prime. In particular, it gives a new value of the object that P accessed, P's new state, whether P halts, and if so, what value P outputs. The prover wins by showing the protocol is incorrect. One way the prover wins is if the protocol responds with a configuration in which the outputs violate the specifications of the task. For example, if the task is k-set agreement, the prover wins if more than k different values were output in configuration C prime, violating the agreement property. The prover also wins if some process outputs a value in configuration C prime, but configuration C prime was reached from an initial configuration in which no process had that value as its input, violating validity. A chain of queries is a consecutive sequence of queries where the resulting configuration of one query is the input configuration to the next query in the sequence. A second way the prover can win is if the protocol allows the prover to continue a chain of queries indefinitely, which shows that the protocol violates weight freedom. Extension-based proofs have one more type of query, which is called an output query. For an output query, the prover chooses a configuration C that it has reached, a set of processes Q, and a possible output value Y. The protocol can respond with a finite sequence of steps by processes in Q, such that starting from configuration C, one of them outputs the value Y. Alternatively, it can say that no such sequence exists. For example, if Q is the set of all processes, then the output query CQ0 asks whether there's an execution starting from C in which the value 0 is output. Likewise, the output query CQ1 asks whether there's an execution starting from C in which the value 1 is output. These two queries tell the prover whether the configuration C is bivalent. After making finitely many output queries and chains of queries without winning, the prover must choose a configuration C it first reached during this phase, and then start the next phase. This next phase is the same, except the prover can only ask queries about configurations that are reachable from C. This keeps on happening until the prover cannot start a new phase, because all the processes have output values and terminated in the configuration it chose. In this case, the prover loses. If the prover asks an infinite chain of queries, or there are an infinite number of phases, the prover has demonstrated that the protocol is not weight-free. An augmented extension-based proof is like an extension-based proof, except that the prover can ask assignment queries instead of output queries. For an assignment query, the prover chooses a configuration C that is reached, a set of processes Q, and an assignment F of output values to a subset Q prime of these processes. The protocol can respond with a finite sequence of steps by processes in Q, such that starting from C, every process Qi and Q prime outputs the value F of Qi. Alternatively, it can say that no such sequence exists. An output query can be simulated by a finite set of assignment queries. Instead of asking whether there is a finite sequence of steps by processes in Q starting from C, in which one of them outputs the value Y, the prover can ask for each process P in Q whether there is a finite sequence of steps by processes in Q starting from C, in which process P outputs the value Y. Thus, augmented extension-based proofs are at least as powerful as extension-based proofs. As I mentioned earlier, Dan, Jim, Rutty, Jimmy, and I showed the impossibility of k-set agreement has no extension-based proof. Our idea was to adaptively construct an adversarial protocol that wins against every prover. Cayman and I used the same technique to show that the impossibility of k-set agreement has no augmented extension-based proof. The essential difference between the proofs of these two theorems is that during phase 1, the adversarial protocol for extension-based proofs only produces configurations in which all the values output are the same, whereas for augmented extension-based proofs, the adversarial protocol may need to produce configurations in which two different values are output. The differences between the proofs of these two theorems is discussed more in the proceedings. Our main theorem says that if there's a reduction from task T to task S, and there is an augmented extension-based proof that T is impossible to solve, then there is an augmented extension-based proof that S is impossible to solve. In the next 9 slides, I'll give you a high-level idea of the proof of this theorem. There are more details in the proceedings. Let P be an augmented extension-based prover that wins against any protocol claiming to solve task T. Fix a weight-free protocol A1 that solves task R1 and a weight-free protocol A2 that solves task R2. Note that if A actually did solve task S, then the composed protocol would solve task T by the correctness of the reduction. We describe an augmented extension-based prover that wins against any protocol A claiming to solve task S. It simulates the interaction between the prover P and the composed protocol. Since P wins against any protocol claiming to solve T, it wins against this composed protocol. We show that this implies our prover wins against protocol A. Suppose that in some step of the simulation of P with the composed protocol, P submits a query C, Q. If Q is taking a step in protocol A1 or A2, then our prover uses its knowledge of these protocols to say what happens. If Q is taking a step in protocol A, then our prover submits a query to A to find out what happens. Now suppose that in some step of the simulation of prover P with the composed protocol, P submits an assignment query, asking if there's a sequence of steps by a set of processes Q, such that starting from configuration C, every process Q in the domain of F outputs the value F of Q. The rough idea is as follows. Using its knowledge of A1, our prover determines which output vectors W can occur in the simulation of A1 from C using only steps by processes in Q. Then, using its knowledge of A2, our prover determines for which input vector Z there is a sequence of steps by processes in Q in the simulation of A2 such that every process Q in the domain of F outputs the value F of Q. Finally, our prover asks a finite number of assignment queries to A to determine whether there is one of these output vectors Z that can be produced from one of these input vectors W. Our prover is actually quite complicated because in the simulated configuration of the composed protocol, some processes may be simulating protocol A1, some may be simulating protocol A, some may be simulating protocol A2, and others will have terminated. For example, in this configuration, processes P1 and P2 are simulating A1, process P3 is simulating A, process P4 is simulating A2, and process P5 has terminated with output 0. Why doesn't this approach work for extension-based proofs? Recall that extension-based proofs have output queries instead of assignment queries. Suppose prover P submits an output query in the simulated interaction with the composed protocol, asking if there is a sequence of steps by processes in Q, such that starting from C, some process in Q outputs the value Y. As before, using its knowledge of A1, prover can determine which output vectors W can occur in the simulation of A1 from C, using only steps by processes in Q. Using its knowledge of A2, again, a process can determine for which input vector Z there's a sequence of steps by processes in Q in the simulation of A2, such that some process in Q outputs the value Y. The problem is, how can a prover determine whether there is one of these output vectors Z that can be produced from one of these input vectors W by asking a finite number of queries and output queries to A? For example, suppose there is an execution in which some process P and Q outputs Y from A2 when P1 has input Z1 and P2 has input Z2. There may be an execution of A from input vector W where P1 outputs Z1, and there may be another execution of A from input vector W where P2 outputs Z2. But there may be no execution of A from input vector W where P1 outputs Z1 and P2 outputs Z2. What does our reduction theorem tell us? There are known reductions from K-leader election and K-test and set to K-set agreement. Since there is no augmented extension-based proof that K-set agreement is impossible to solve, it follows from the contrapositive of our reduction theorem that there are no augmented extension-based proofs that K-leader election and K-test and set are impossible to solve. These facts were not previously known. A protocol is anonymous if all processes with the same input value behave the same way. In other words, what they do does not depend on their identifiers. It is known that there are no anonymous weight-free protocols for solving weak symmetry breaking or 2n-2 renaming among n greater than or equal to 2 processes in asynchronous shared memory systems where processes communicate using registers. The proofs of these two results also use combinatorial topology. An open question that was posed in my earlier paper with Dan, Jim, Rutty, and Jimmy is whether these results have extension-based proofs. It is straightforward to extend our reduction theorem to anonymous protocols. If there is an anonymous reduction from task T to task S, and there is an augmented extension-based proof that T is impossible to solve anonymously, then there is an augmented extension-based proof that S is impossible to solve anonymously. Moreover, our proof that there is no augmented extension-based proof that case-set agreement is impossible to solve can easily be extended to show that case-set agreement is impossible to solve anonymously. Since there are anonymous reductions from weak symmetry breaking and 2n-2 renaming to n-1 set agreement, it follows that there are no augmented extension-based proofs, and hence no extension-based proofs of the impossibility of solving weak symmetry breaking and 2n-2 renaming anonymously. There are a number of open problems that remain. The first is to extend our reduction theorem to include oracle reductions, which may involve solving multiple instances of the problem being reduced to. Our reduction theorem only applies to tasks with finite input domains. Another problem is to extend it to tasks with infinite input domains. Finally, is the class of augmented extension-based proofs strictly more powerful than the class of extension-based proofs? In other words, is there a task for which there is an augmented extension-based proof that is impossible to solve, but there is no extension-based proof that is impossible to solve? Thank you for watching this talk. I look forward to answering your questions during the conference.